Okay, today we're going to talk about operations as they pertain to radical expressions. So using radical expressions and the four basic operations that we've talked about with other algebraic expressions. First, I want you to take a second and pause the video for 90 seconds, 2 minutes, and try to simplify both of these radicals as much as you can. We have the square root of 12c to the 6th d cubed, and the cube root of 27 x to the 12th y to the 7th. So pause the video, simplify these as much as you can, and then come back. Okay, first thing we want to do is factor this. We want to factor this in a way that we can get perfect squares. So I'm thinking about the factors of 12, and I'm looking for perfect squares. Factors of 12 are 1 and 12, 2 and 6. None of those are perfect squares. Or 3 and 4. And 4 is a perfect square. C to the 6th, I'm going to factor all of the variables into pairs, as many pairs as I can get. So if I factor out a c squared, what's left? Well, there would be 4 more c's still, right? There's 6 of them total. If I pair 2 of them out, that means there's 4 left, which I could write as another c squared. Now I've taken care of 4 of them out of the 6, which means there's another pair, right? So 6 c's here, and there's still 6 c's here, so it's all the same. D cubed, I can take out 1 pair of d's, but that means there's 1 d left over, right? All of this is still inside the radical. So now I'm going to go through and just take the square roots of the things that I can take the square roots of. So for example, square root of 3, I don't know what that is. We're going to leave the 3 inside the radical. The square root of 4, though, is a 2. So I'm going to take the square root and bring it outside the radical. The things I take the square roots of come out in front. The square root of c squared, well, that's c. Square root of c squared is another c. The square root of c squared is another c. Square root of d squared is a d, and I can't take the square root of this last d, so it's going to stay in the radical as well, which means inside the radical I have 3d, right? 3 and d. Now I'm just going to simplify this a little bit more. I have 2. C times c times c is c cubed times d times the square root of 3d. That is the same value as the original radical, but it's been reduced and simplified. Okay. Same thing on the second one, but this time we're talking about cube roots, right? So I want to factor things into triples, groups of 3, not pairs. So 27, let's say I don't know how to factor that. One thing we can do is what's called a factor tree. Think of one factor of 27. Well, that's 3. Let's see, 27 can factor into 3 and 9. That's not a 9. 3 can't be factored, it's prime. 9 can be factored into 3, and those can't be factored because they're prime. So 3 times 3 times 3 is 27. So 3 times 3 times 3, right? Or 3 cubed, and there's that grouping of 3 we talked about. So I'm going to start grouping the variables into groups of 3. So if I take an x cubed, out of the x to the 12th, that means there's 9 left, so I can take out another x cubed. That's 6 of them, right, out of the 12. And another 3, and another 3. Now just make sure when you're done, this means there's 12 x's being multiplied together, correct? Well, here's 3 x's, another 3 x's, another 3, and another 3. Throw 3, 6, 9, 12 x's being multiplied together. Do the same thing with the y's. As I start taking out these groups, I can think about subtracting them. Right? If there's 7 total, I've taken care of 3. That means there's 4 left, so I can do another group of 3. That's a total of 6 y's, which means there's 1 left. All of this still inside the radical. Now I'm going to start taking square roots of things that can have, cube roots of things that have perfect cubes, right? So the cube root, because remember this is cubed, the cube root of 3 cubed is 3. Cube root of x cubed is x. Cube root of x cubed is another x. Another x cubed gives me another x, and another x cubed gives me another x. There are 4 x's out front now. I can do the same thing with 2 of the groups of y's. There's a y and another y. This y I can't take the cube root of, so it's going to stay inside the radical. So all that's left is 3. There's 1, 2, 3, 4 x's and 2 y's times the cube root of y. Okay? Remember the properties of square roots we talked about, those are still true of nth roots. So if it's the cubed root, the 4th root, the 57th root, it doesn't matter. As long as the index of the root, meaning this part, these are square roots, but they could be cubed roots, as long as the index is the same, I can multiply the radicands, the thing inside the radical, right? So the square root of 2 times the square root of 8 is the same thing as the square root of 16. the cubed root of 3 and the cubed root of 9 is the same as the cubed root of 27 if they're being multiplied. So I can either do them separately or I can multiply them together. Those properties hold true. That's going to be important. The quotient property also works. So if I'm taking a radical, if there's a fraction inside the radical, I can take that radical of the top and that radical of the bottom. So if I'm doing the nth root of a over b, that's the nth root of a over the nth root of b, as long as, right, we're doing a positive root. We're not talking about negative roots. So for example, I've got the square root of 27 over the square root of 3. I could think of that as the square root of 9 because I can take the square root of 27 thirds, which is the square root of 9. That's a step they're not showing. But if I divide 27 by 3 first, that gives me the square root of 9. Same thing here. This one's a little bit more complicated. This is a situation where we might actually use this property. I've got the cube root of x to the 6th over 8. Well, that's the cube root of x to the 6th over the cube root of 8. So the cube root of 8 is 2, right? 2 cubed is 8. A couple ways we can do this. We could break it into the pairs like we did on the example. Or I'm really dividing these. I'm taking the cubed root of x to the 6th, which means x to the 6 thirds. Well, what's the 6 thirds? That's just 2, right? So I get x squared. So x squared over 2, or 1/2 x squared. The new thing that is something we're going to be dealing with today is what we call rationalizing the denominator. We can't have fractions inside a radical, and we can't have radicals in the denominator. Okay, so here's a couple patterns just showing that. I would not worry so much about the first two columns, but focus on the examples because those are going to be ones that will make a little bit more sense, I think. So in the first example, we've got a square root on the bottom. And I can't have a square root on the bottom, so how do I undo the square rooting of something? Well, I need to square it, right? I'm going to multiply it by itself. So I'm going to multiply by another square root of 3. But if I multiply the bottom by square root of 3, I have to multiply the top by square root of 3, so that the value of the fraction is still just a 1. And then I simplify. Square root of 3 times square root of 3 is 3. And then I have 2 times the square root of 3. So this is the exact same thing as this, but it follows the simplification rules for radicals. Okay, same thing here. I've got a cube root. The problem is I only have 1, 2, and I need a group of 3 of them, right, to take a cube root. So I'm going to have to multiply by the cube root of 2 more 2's. So I end up with the cube root of 2 cubed. We'll do an example like this that might make a little bit more sense here in a minute. So I'm sure you're all thinking, why do we do this, right? Why would we worry about that? This came about in a time when calculators didn't exist. So it was very difficult to have radicals in the denominator of a fraction. Nobody knew how to divide by a radical. It made it a lot easier if everything was in the same format. So if everybody agreed, hey, we're not going to put radicals in the denominator, we're not going to have fractions inside a radical, it made sure that when people were looking at each other's work, it would all make sense and they would understand what they were doing. So because of the lack of calculators, they all settled on a format that was the same. And then the only reason we're really worrying about it is this guy. The ACT still does questions on the rationalization of the denominator. Obviously, you can type these things into your calculator the way they are if you actually have to do one. The calculator can handle it just fine, but the ACT does have questions about rationalizing the denominator, which is why we're still going to go over it. So let's tackle this guy. I got the square root of x to the 6th over the square root of y to the 7th. Okay, so let's simplify as much as we can. This can be the square root of x to the 6th over the square root of y to the 7th. Now what we're going to want to do is multiply the bottom by itself, because if I multiply by another square root of y to the 7th, I will just have y to the 7th. If I take a square root and multiply by the same square root, it's like I'm squaring it, and I get rid of the square root. The square root cancels. But if I multiply the bottom by that, I have to multiply the top by that also. Okay, so remember when we multiply fractions, we multiply the numerators, we multiply the denominators. So the denominator is going to be the square root of y to the 7th times the square root of y to the 7th, which is just y to the 7th. The numerator is the square root of x to the 6th, y to the 7th. Okay, we talked about if the index is the same, you can just multiply the radicals together. So that's what I'm going to do. Then we can simplify this a little bit. Right? What's the square root of x to the 6th? That would be x cubed. X to the 7th, or y to the 7th, excuse me, could be y squared, y squared y. So I have 3 perfect squares, so that can become y cubed with just 1 y left over y to the 7th. I have 3 y's on top and 4 in the bottom, or 7 in the bottom, which means this can just be x cubed square root of y all over y to the 4th if these 3 cancel out with 3 of those. So this would be the simplified version. I know that's a lot of work, and it seems a little silly when it actually doesn't necessarily even look simpler than the original. But again, it's just a process that needs to be learned. It's on the ACT. It's just good to be able to handle radicals and do these operations. So think of it more as practice with operations on radicals rather than the end product being what we're necessarily worried about. Okay. This was a little bit different because it's the 4th root. Okay, so let's just split it up first. Let's call it the 4th root of 6 over the 4th root of 5x. I can't have a radical in the bottom, so I'm going to have to multiply by the 4th root of something to get rid of it. But if I just do 5x, I'm going to end up with the 4th root of 5 squared x squared. That's not enough. If I'm going to take 4th roots, I need things to the 4th power. So I need to multiply by 5 cubed x cubed in the top and bottom. And we'll go through why here in just a second. So I'm multiplying by this, right? So let's jump down here. In the denominator, I have the 4th root. 5 times 5 cubed is 5 to the 4th. X times x cubed is x to the 4th. So that's the denominator. Then up top, I'm just going to have one radical. 4th root of 6 times 5 cubed x cubed. Okay, so if we look at the bottom, the 4th root of 5 to the 4th is just 5. The 4th root of x to the 4th is just x. So that entire denominator is now just 5x, which is good, because now I don't have any radicals down there. The top is a little bit messier. It's the 4th root. 5 to the 3rd is 125. 5 times 5 times 5. And if you multiply 125 by 6, we get 720 x cubed. You would want to check to see if 720 is a perfect 4th. It is not. I'm just going to leave it like that. This is simplified because the denominator does not have any radicals in it, and I don't have any fractions inside the radical. I realize I have a fraction, and my final answer there may not be the cleanest thing, so let me rewrite it. 720x cubed. The fraction contains the radical, not the other way around. It is not this. This would not be simplified, and we could not leave it like this. Not that these are the same thing, but this is what's not okay. You can't have a fraction inside a radical. I have a fraction where the numerator has a radical. The denominator does not. This is okay. This is good. This is bad. Okay, same thing here. This time we're just simplifying the radical itself. We're not dividing. We've got the multiplication product here. 5 and 3 are both outside the radical, so I'll multiply those together. That's not so hard. That's 15. Then I have the cubed root of all of the rest of this. So we're just going to multiply this together as we go. So I've got negative 12 times 18, which is negative 216. Negative 216. So those have been handled. A and a squared is a cubed. B and b squared is b cubed. That's a good sign. I'm taking cube roots. I've got cubed things. That's nice. We're going to want to factor this as much as possible. So I'm going to check to see if 216 is a perfect cube. So the way to do that, type in negative 216 into your calculator in parentheses and raise it to the 1/3 power. So I'm going to do that right now. Parentheses, negative 216, close parentheses. Caret, which is right above the division sign, open parentheses, 1 divided by 3. I got to make sure everything's in parentheses. Oh, and guess what? The cube root is negative 6. So this is negative 6 cubed, a cubed, b cubed. I'm taking the cube root of all that stuff, and everything's cubed, so that's great news. This is going to be 15 times negative 6, right, because the cube and the cube root cancel. A, because the cube and the cube root cancel, times b, because the b cubed and the cube root cancel. So now I just need to do 15 times 6, which is going to be 90. I have negative 90a b. Now it's negative. You might be thinking you can't have negative roots, but remember that's only for even roots. I can't take a square root or a fourth root and end up with a negative number. But I can take a cubed root because it's odd. Negative times a negative will give me that original negative, which is just fine. Last but not least, radicals can be added and subtracted if and only if. When you see an if with two f's like this, it means if and only if. It's a logic shorthand. So radicals can be added and subtracted if and only if they are like terms. So the blue circle is an example of a like term because I have the same index. They're both square roots and the same radicand. They're both square root of 3b. These are both the root of 3b, but this one's a square root and this one's a cubed root. So those are unlike, right? These are both square roots, so that's a good sign, but I have different radicands, so those are unlike. I can only do it if they have like terms. Now, if I have something bigger like this, square root of 98 minus 2 root 32, they certainly don't look alike, but they're also not reduced. So let's start with the 98. Let's say I don't know what goes into 98. Let's pick something. Well, it's even, so it's got to be divisible by 2. 2 times, what, 49? 49 could be 7 and 7. As soon as you recognize a perfect square, you want to use that. But if not, it would have worked out. It turns out those are the only factors of 49. So the square root of 98 can be 2 times 7 squared, right? 2 times 7 times 7 minus 2. Now 32. Again, let's pretend we don't see factors right away. Some of you might, and that's great. 2 goes into it because it's even, so that's 2 times 16. Hey, I see another perfect square here. That's 4 times 4. So this guy is 2 times 4 squared. So when I take out the perfect squares, right, square root of 7 squared is 7. And the square root of 4 squared is 4. So that 4 comes out here. Times the 2 means it's minus 8 root 2. Now all of a sudden, they are like terms because I have the same index. They're both square roots. And the radicands are the same. They're both the square root of 2. So I have 7 root 2's minus 8 root 2's. It doesn't really matter what the radical is. I have 7 of something, and I'm subtracting 8 of the same something. 7 minus 8 is negative 1 of that thing. Negative 1 square root of 2, or just negative square root of 2, depending on which way you like to write that. And so we only want to judge radicals as being like or unlike after we simplify and reduce their radicands as much as possible. Okay, multiplying. So same thing, we're just going to have to distribute, right? I've got 2 terms here. So everything gets multiplied by this guy. So that's 6. Oops, let me undo that. 6 times 2 is 12. Square root of 3 times square root of 3 is the square root of 9. We'll come back and take care of that in a second. And multiply this guy by the second term. 6 times 4 is 24. Notice I'm multiplying the stuff outside of the radicals and then multiplying the radicals together. Square root of 3 and square root of 2 is square root of 6. We can do that because they're both square roots. If one of these was a cube root, we'd be in big trouble. Okay, I'm going to switch colors and do the negative 5. So negative 5 times 2 root 3. Negative 5 is outside the radical, so that's negative 10 root 3. And then negative 5 times 4 root 2. Well, that's negative 20 root 2. So now we got to go back and look at our like terms, figure out what's the same and what isn't. Okay, so I'm going to simplify everything that I can. Square root of 9 is just 3. That's 3 times 12, so that's 36. Square root of 6 I can't do anything with because I've got square root of 2, or 2 times 3 are the only factors. Neither one of those is a perfect square. So I'm going to leave this as 24 root 6. Minus 10 root 3 minus 20 root 2. This would be one way of writing it, but what I can do here is change this a little bit. We could call this 36 plus, let's say, 4 root 2 times 6 root 3. Now, if you'll notice, it has to be a times, right? So even though we can split this up, it doesn't help us combine anything. Right? I just wanted to point out that this could be factored. I can factor the front number. It could be 4 and 6, or 3 and 8, or 2 and 12. However I want to do that, I could pick any combination of those. And the square root of 6 could be factored as square root of 2 and square root of 3. which seems helpful because I've got square roots of 2's and square roots of 3's. But remember, we're adding and subtracting. This is multiplication. That doesn't actually help, right? So this is, oops, that's a terrible circle. That's the only way to write this. So our simplified answer is going to be 36 plus 24 root 6 minus 10 root 3 minus 20 root 2. That's going to be as simplified as we can get the product of these two expressions. It's just like multiplying, just like foiling. We got to just go through the process of multiplying the stuff outside the radicals and then the stuff inside the radicals. Okay. Last thing I want to talk about. Binomials of this specific form, a square root of b plus c square root of d, and a square root of b minus c square root of d, are called conjugates. It's a lot easier to see if you see an example with numbers. So let's use the denominator here. Square root of 5 minus 1 and the square root of 5 plus 1. These are conjugates of each other. They're the exact same thing, but the sign in the middle has changed. So we can use these to rationalize a denominator, right? If we want to get rid of that square root in the bottom, which we're going to need to do, we have to do it with conjugates. So what I'm going to multiply the bottom by is the square root of 5 plus 1. And the top, square root of 5 plus 1. Okay, so now I'm multiplying these. We multiply straight across. Square root of 5 times square root of 5, that's the square root of 25. Square root of 5 times 1 is a positive root 5. Negative square root of 1 times 5 is a negative root 5. You can see where this is going. Negative 5, or square root of 5 plus 1 times plus 1 is square root of 5. I'm sorry, we did that already. 1 times 1. I hope some of you caught that. I was wondering what was going on here. Give me just a second. We did square root of 5 times square root of 5. That was square root of 25. Then square root of 1 is this guy. 1 times that is this guy. And then 1 times 1. So that's minus 1. There we go. Combined stuff. Square root of 25 is 5. Plus root 5 and minus root 5, those cancel. Minus 1. 5 minus 1 is 4. So the denominator here is just a 4. And then in the top, I just distribute the 2. So 2 root 5 plus 2. Always look to reduce any more. I could take a 2 out of everything. So this could be root 5 plus 1 all over 2. That would be as simple as it gets. Okay. Go ahead and rewind any of this to any part that you want. You're on to the homework, and good luck.